Yes, binary trees are an extremely important subject in computer science. They are not graphs, and graphs have nothing to do with them. They are completely different concepts. A tree vertex can have any number of connected vertices. By the other hand, a binary tree only can have a right child, a left child, or both childs. There may exist binary trees with more than two childs called B-trees. Watch out, because they look similar to graphs. In this unit we only take care of binary trees up to two childs. So, if isn't a graph, what is a binary tree? Is a set of nodes such that each one usually holds information and the references of its successors, similar to linked lists. That node will be called the parent, predecessor or ancestor, and the child's successors or descendants. Each successor is considered a subtree by itself. Trees are called similar only if they have the same shape. If a node has no childs, it is considered a leaf or terminal. Now, the reason why binary trees are used is efficiency as usual. The time complexity of a binary tree is the logarithm in base 2 of n, where n is the number of nodes. By example, in a linear search for a specific record among 1,000 records has 1,000 time complexity. By the other hand, a binary tree time complexity is the logarithm in base 2 of 1,000. This equals to 10, 100 times faster. Most databases engines uses binary trees to arrange data. At the time we run the algorithms to work later inside this structure, let's discuss binary trees from best to worst in performance terms. A perfect binary tree with a symmetric structure where each level is called a generation always matches these conditions, and the time complexity is the logarithm in base 2 of n. If the height of the left and right subtrees for any node does not differ by more than 1, then it is said to be a complete binary tree and still have this time complexity. Now, if the difference for any node is more than 1, then it is said to be unbalanced binary tree, and the performance is very low, to the point it has no sense to work with. So there are two ways to deal with unbalanced binary trees. The first, for the long run, is to apply some kind of balancing algorithm. This will be something like this. Let's assign some kind of order, then divide and conquer. If the middle element is not present, take the left one, like the numbers 2 and 7 for the left and right subtrees roots respectively. Also exists a quick solution to extend the tree ensuring a balanced structure. Just insert empty boxes. This is called an extended binary tree or a two-tree. Here, these three conditions are present. When working with big amounts of data, any solution will be slow anyways. Try to avoid unbalanced trees. Now, how binary trees are stored inside the computer memory? This is done via linked list, where each node is accessed by a numeric or alphanumeric index, in such a way that every element keeps the indexes of their childs. Otherwise, it will store a null pointer. There is no need on walking the entire structure one by one searching for an element, so do not confuse it with linear arrays. When values are unique, indexed, and the tree is balanced, it is called a binary search tree. All nodes will follow this condition, making it the most efficient way to insert and retrieve information. By example, we are searching for the node which contains 20. Input 20 and the root node into this recursive function. Now, these 4 conditions will be read by the compiler from up to down, one by one. 20 not equal to 19, so this will not be executed. Next, 20 isn't less than 19, this will not run either. Next, 20 is greater than 19. Here we call the search function again, this time with 20 and 28. This time we go to the left child of 28, which contains 20. At the fourth call, the function will return 6, where 20 is located. If the value is less or greater than a node with no childs, then it's not found. Remember, leaf nodes contains null childs. The insertion process works similar. By example, let's insert the number 13, input 13 and the root node into the function. This condition will run and the function will be called again, this time for the left subtree, again for the right one, and here a new subtree with 13 will be created. All methods we have seen until now were for binary search purposes. Also, we need to use other techniques. Let's discuss how binary trees are traversed. The preorder traversal will read data in the subtree root node and then go to the childs from left to right. The inorder traversal will read data inside the left child and the root node before the right one. Finally, the postorder traversal starts on the childs from left to right before the root node. The process for delete a node of a tree must rearrange the structure to do not affect the conditions. It will look something like this. Define a function which holds 4 conditions. First case, we want to delete 13, which is not there, so exit. Second case, we want to delete the node with 30. This one has no childs, so it's just be wiped out. Third case, we want to delete 9, that has one single child. It will be replaced by its only child. And in the fourth case, we want to delete 19 with 2 childs. First of all, who is the inorder successor of target? This is 28. If that successor contains a left child, by example 22, it will be the replacement for the target. If not, the replacement will be the successor itself. As you see, this case holds 2 cases that only will run along with the fourth condition. This is known as nested condition. Heaps are a special case of binary trees, arranging the elements in such a way that every ancestor is greater or equal than its successors. This is known as maximum heap. The process for insertion begins with append a new element to the end, and while this condition is true, the new value will be swapped by its parent, ensuring the integrity. The deletion process starts with swapping the last value, which is 14, with the element to be deleted. By example, we want to delete 44, and while this condition remains true, this value will be swapped by its greater successor. This is useful to maintain a numeric order. By example, if we were about to classify millions of bank customers by its opening amount, it would be far better to arrange the information in a heap, making every operation hundreds times faster. Now, using the same idea, we can arrange elements numerically from lowest to highest. In such a case, it is called a minimum heap, where the insertions and deletions works the same way. Assigning weight helps optimize tree traversal algorithms. By knowing the weight of a node, we can determine the relative position of its children and navigate the tree efficiently. A node with 2 children has a weight of 3. A node with 1 single child has a weight of 2. A leaf node has a weight of 1, and the total weight of these 3 is the sum on all individual weights. For example, here the total weight is 11. Now, the weighted path length only applies for leaf nodes in weighted binary trees. By example, let's suppose we are using a tree like this. The combined path length is 49, 44 for the left and 5 for the right subtree respectively. It is important to maintain a weighted balance structure along with a high balancing. These can be rearranged like this to ensure efficiency. Weights are used to reduce the size of a file. Consider a file containing a sentence in ASCII code. The size is 33 bytes. In order to use it, this is what a processor must manage. Let's begin with tokenize this sentence. Now we have 16 objects. Each one holds a unique symbol and their frequency. By example, the string contains 3 D characters and 6 blank spaces. In the next step, depict a weighted tree maintaining weight balance using a grouping algorithm like this. This ensures faster access to the most frequent symbols. By example, we only need 3 actions to reach a blank space and 5 to get the A character. This is what it looks into the new custom encoding system. The weighted path length, which is 118, denotes the new size. This is 118 bits or 15 bytes. To decode the file, just organize a queue and use some kind of algorithm like this. Here we take the first element and the root node. The root node isn't a token, hence the first condition not executed. Next, the first element is not 0. Next, the element is 1. So call the function again, now with the last node right child along with the next element in QE, which is 0. This time we navigate to the left child. When a token is found, then a character is decoded, and while element in QE, the function is called again until be exhausted. Now the encoded message has to be sent along with this construct. Despite costs, reduce the payload always will be a good plan. Another important application of binary trees occurs when operating systems requires to allocate the data in real time. Let's begin with a typical device executing applications. Those apps work inside the random access memory. The reading and writing is made by a processor, and also we have a storage unit where everything is saved. Let's denote those apps as boxes. We agree that a device is just a system that reads and writes bits, so let's denote those apps as pages containing bits. The random access memory is divided into segments. A segment cannot contain a program by itself. That's why the operating system uses a group of random segments called frames to work together and contain the entire application. Applications may run in the background using some kind of entity called virtual RAM. A VRAM usually has a binary tree with each segment address, intending to emulate a random access, which occurs between the processor and the physical memory via multiplexing.